You clicked on this video because you know the fundamental flaw in how robots learn today. They are stuck in a cycle where mastering a new skill instantly erases the old ones they already possessed. This is the catastrophic forgetting problem, and it is the single biggest barrier preventing robots from becoming true lifelong learners. By the end of this explanation, you will understand the specific engineering breakthrough that turns rigid systems into adaptable agents capable of continuous improvement without losing their memory. For years, the standard approach to training robotic foundation models has been supervised fine-tuning. This process is fundamentally off-policy. It works by feeding the model a new dataset and forcing the weights to adjust to match the new targets. The problem is that the model has no mechanism to remember what it learned before. When you train a model to pick up a cube, it learns the weights for that specific motion. When you then train it to stack blocks, the mathematical updates required for stacking overwrite the specific weight configurations needed for picking up the cube. The result is a performance curve that spikes on the new task but plummets on the old one. The robot forgets how to pick up the cube because the new task demanded a different set of neural pathways. This creates a production nightmare. If you want a robot to learn a sequence of 10 skills, you cannot simply feed it the data for skill number 10 and expect it to retain the first 9. You would need to store massive replay buffers of every single past interaction, retraining the model on old data every time it learns something new. This approach is computationally expensive and requires storage architectures that are often infeasible for edge devices or autonomous systems operating in the field. The trade-off has always been between learning speed and memory retention. You could not have both with standard fine-tuning. The breakthrough comes from a method called self-distillation fine-tuning. This approach fundamentally changes the training loop from an off-policy overwrite process into an on-policy self-reinforcing loop. Instead of treating the model as a blank slate for each new task, the system utilizes a demonstration-conditioned version of the model as its own teacher. The model generates on-policy training signals through in-context learning, effectively creating a stable memory buffer without the need for external data storage. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the core mechanism. When the robot encounters a new task, it does not just learn from the raw demonstration data. It also generates its own predictions based on its current internal state. These predictions serve as soft targets for the learning algorithm. The model is penalized not just for failing the new task, but for diverging from its own previous behavior on tasks it has already mastered. By maintaining the probability distributions of old skills while updating for new ones, the system stabilizes the loss landscape. The weights shift just enough to accommodate the new skill but remain anchored to the prior knowledge. This method eliminates the need for explicit reward functions that are typical of reinforcement learning. In many robotic domains, defining a precise reward function is incredibly difficult. You might know what a successful pick looks like, but quantifying that success into a mathematical signal that drives learning is a complex engineering hurdle. Self-distillation fine-tuning bypasses this entirely. It relies on the availability of expert demonstrations, which are often easier to collect than the precise reward signals required for reinforcement learning. The empirical results from the research teams at MIT and ETH Zurich are compelling. They demonstrated that this method consistently outperforms standard supervised fine-tuning. The model achieved higher accuracy on new tasks while preserving prior capabilities. In their benchmarks, the system showed no performance regression on previously learned skills after being introduced to a sequence of new tasks. This is the first time we have seen a single foundation model accumulate a sequence of skills without the typical forgetting curve. However, this solution introduces a new engineering trade-off. While it removes the storage and retrieval overhead of replay buffers, it introduces a latency bottleneck during the training phase. Because the model must generate its own on-policy trajectories for every update step, the computational cost per training iteration is higher than static fine-tuning. The system has to run inference to generate the soft targets before it can update the weights. This means that for real-time applications where immediate adaptation is required, the latency introduced by this self-distillation loop could be a limiting factor. The implication for robotics engineering is profound. We are shifting the architectural dependency from managing complex data pipelines for replay storage to optimizing the model's internal consistency. This makes the approach viable for edge devices with limited memory where storing historical data is simply infeasible. A robot operating in a remote location can learn new skills on the fly without needing to upload gigabytes of past data to a cloud server. It can adapt to its environment continuously, mimicking the human ability to improve over time without losing the skills we learned in childhood. Yet, we must remain intellectually honest about the current state of this technology. The evidence is currently limited to specific skill learning and knowledge acquisition benchmarks. There is no long-term data on extreme sequential learning scenarios where a model must learn hundreds of skills over months of operation. We do not yet know if the stability holds when the number of tasks becomes massive. Furthermore, while the approach mimics human-like continuous improvement, the reliance on in-context learning may introduce computational overhead that scales poorly with the number of tasks. The path forward requires balancing the elegance of the self-distillation loop with the physical constraints of real-world hardware. If we can optimize the generation of on-policy trajectories, we can unlock the potential for robots that are not just tools, but partners that grow with us. The rigid systems of the past are giving way to adaptable agents. The future of robotics is not about building a new robot for every new task. It is about building a single foundation that can learn, adapt, and remember. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.